16 plus 9, that is 25, plus 1, that is 26, plus 4, so 30. So norm u is equal to 30. And what is norm v? Norm v is equal to under root 4 plus 1, that is 5, plus 4, that is 9, plus 9, that is 18. So norm u is equal to under root 30 and norm v is equal to under root 18, correct? So the calculation of cos theta, that is equal to inner product uv upon norm u norm v, that is equal to minus 9 upon under root 30 under root 18. Okay. So find the maximum and minimum values of the quadratic form x1 square plus x2 square plus 4x1 x2 subject to the constraint. Next question, right? Plus x1 square plus x2 square, that is equal to 1. Determine values of x1 x2 at which the maximum and minimum occurs. So we are given that quadratic form q is equal to x1 square plus x2 square plus 4x1 x2. So from this quadratic form you can define a matrix, right? X1 square and x2 square, the coefficient of x1 square and x2 square is 1, so that's why the main diagonal is 1 1. And this 4x1 x2, the coefficient of x1 x2 is 4, so that's why we have to divide this 4 divided by 2, and that is another diagonal entries 2 2, correct? So the matrix associated with the quadratic form q is A is equal to 1 2 2 1. Now we have to find the characteristic equation, eigenvalue, eigenvector, right? And then using that eigenvector and eigenvalue we can find the maximum and minimum occur, right? X1 x2 at which the maximum and minimum occur. So first of all find the characteristic equation of the given matrix. So let's see, 1 2 2 1. The characteristic equation of A is given by lambda square minus trace of A into lambda plus determinant of A, that is equal to 0. So lambda square minus trace of A means the sum of the main diagonal entries. So 1 plus 1, that is 2. So lambda square minus 2 lambda plus determinant. What is the determinant? 1 into 1 1 minus 2 into 2 4. So 1 minus 4, that is minus 3. So lambda square minus 2 lambda minus 3, that is equal to 0. Lambda minus 3 into lambda plus 1, right? The factor of this two part, factor of this equation, you will get lambda minus 3 into lambda plus 1, that is equal to 0. So the eigenvalues of A are 3 and minus 1. The eigenvector x, that is equal to x1 x2 corresponding to the eigenvalue lambda is equal to 3 is given by the matrix equation A minus lambda I into x, that is equal to 0. So A minus 3i into x, that is equal to 0. So what is A minus 3i? That is minus 2 minus 2. Just put the value lambda is equal to 3 in this equation, or just A minus 3i. So what is our A? 1 2 2 minus 1 and minus 3i, that means 3 0 0 3. So 1 minus 3, that is 1 minus 3, that is minus 2, right? 2 minus 0, that is 2. 2 minus 0, that is 2, and again 1 minus 3, that is minus 2. So definitely A minus 3i into x is equal to 0. You will get minus 2 minus 2 into x1 x2, that is equal to 0 0. Now when we multiply this matrix, we have to convert this matrix into a row echelon form. So when we multiply first row with 1 and add into the second row, you will get minus 2 0 0 into x1 x2, that is equal to 0 0. Okay, so using this equations you will get minus 2x1 okay, minus 2x1 plus 2x2, that is equal to 0. So in other words you can also say 2x1 minus 2x2, that is equal to 0. So you will get x1 is equal to x2. So taking x1 is equal to 1, you will get x2 is equal to 1 also. So the eigenvector corresponding to lambda is equal to 3 is 1 1. Now the normalized form of x1, that is equal to, this is our x1 1 1 1. Normalized form is x1, that is equal to 1 by root 2 1 by root 2. We have to divide norm of this vector. What is the norm of this vector? Root 2. Okay, so that's why we have to divide it by its norm, 1 by root 2, 1 by root 2. The eigenvector corresponding to the eigenvalue lambda is equal to minus 1 is again given by the matrix equation A minus lambda I into x, that is equal to 0. Okay, put lambda is equal to minus 1, so you will get A plus I into x is equal to 0. Now what is our A? 1 2 2 1 plus I means 1 0 0 1, so 1 plus 1 2, 2 plus 0 2, 2 plus 0 2, and 1 plus 1 2. So again you will get 2 2, the first row is 2 2, the second row is also 2 2, x1 x2, that is equal to 0 0. Now to convert this matrix into a row echelon form, we have to multiply first row with minus 1 and add into the second row. So you will get the first row is 2 2 as it is, and second row become 0 0. So 2 2 0 0 into x1 x2, that is equal to 0 0, right? We multiply first row with minus 1 and add into the second row. From this matrix we get 2x1 plus 2x2, that is equal to 0. So x1 is equal to minus x2. Taking x1 is equal to 1, you will get x2 is equal to minus 1. Okay, so the eigenvector corresponding to lambda is equal to minus 1 is 1 minus 1. Its normalized form, again we have to find the normalized form x2. So the normalized form x2 is 1 by root 2 minus 1 by root 2. Okay, so this is our x1, 1 by root 2 1 by root 2, and this is our x2 normalized vector, 1 by root 2 minus 1 by root 2. Okay, and lambda is equal to 3 is the largest eigenvalue of A, hence the maximum value of the quadratic form Q subject to x1 square plus x2 square, that is equal to 1, is 3, and it occurs when x is equal to 1 by root 2, 1 by root 2, and when x1 is equal to 1 by root 2, x2 is equal to 1 by root 2. Now next is lambda is equal to minus 1 is the smallest eigenvalue of A, hence the minimum value of the quadratic form Q subject to x1 square plus x2 square is equal to 1 is minus 1, and it occurs when x is equal to x2 equal to 1 by root 2 minus 1 by root 2. When x1 is equal to 1 by root 2, x2 is equal to 1 by root 2. So here the complete the solution of this question. Next question, question 5b. Find the least square solution of the linear system Ax is equal to b, given by x1 minus x2 is equal to 4, 3x1 plus 2x2 is equal to 1, minus 2x1 plus 4x2 is equal to 3, and find the orthogonal projection of B on the column space of A. So this question asked in 5 marks. The matrix form of the given equation is from the first equation we have to make first row 1 minus 1, from second equation 3 2, from the third equation minus 2 4, into x1 x2, that is equal to b. B is 4 1 3, so 4 1 3. Ax is equal to b. Okay, Ax is equal to b, where A is equal to 1 minus 1 3 2 minus 2 4, x is equal to x1 x2, and b is equal to 4 1 3. Okay, so A transpose, we need A transpose, so this is our A transpose, 1 3 minus 2, 1 3 minus 2, and minus 1 2 4, minus 1 2 4. The normal equations are given by A transpose A x caret, that is equal to A transpose B. Okay, so A transpose, that is 1 3 minus 2 minus 1 2 4, A is 1 minus 1 3 2 minus 2 4, x1 x2, that is equal to 1 3 minus 2 minus 1 2 4, 4 1 3. Okay, so that's why this multiplication of these two matrices, you can see 1 into 1 1, plus 3 into 3 9, plus 4, so 9 plus 4 13, plus 1 14, again 1 minus 1 plus 6 5, minus 8 minus 3, so 14 minus 3, right? Similarly you will get the second row, that means the multiplication of these two matrices, the first row is 14 minus 3, and the second row become minus 3 21, x1 x2, that is equal to multiplication of these two matrices. This is 2 cross 3 matrices and this is 3 cross 1 matrices. So definitely see 1 4, 1 into 4 4 plus 3 into 1 3, so 4 plus 3 7 minus 6, that is 1. Then minus 4 plus 2 minus 2 plus 12, that is 10, so 110. x1 x2 that is equal to 14 minus 3 21 inverse into 110. So inverse of this matrix, right? Again the 2 cross 2 matrix, and we have to find the inverse of that matrix. It's quite simple, just we have to interchange the main principal diagonal element 21 and 14 become interchange, and the sign of the another diagonal, that is minus 3 become 3 3. So 21 14 3 3, and then divided by its determinant. What is its determinant? 14 into 21 minus 9, so that is 285. Okay, 110, that is equal to 1 upon 285. Then multiplication of this two matrix, that is 51 143, and finally you will get 17 by 95 and 143 by 285, right? So the least square solution is x1 is equal to 17 by 95 and x2 is equal to 143 by 285. Also we have to find the orthogonal projection of B on the column space of A. So that's why that is given by AX. A is our given matrix, 1 minus 1 3 2 minus 2 4. X is this 17 by 95 and 143 by 285. So finally you will get this column vector, that is minus 92 by 285, 439 by 285 and 94 by 57. So here the question 5b is complete. Now the next question 5c, first part. Let R3 have the Euclidean inner product for which values of k are u and v orthogonal, where u is equal to k k1, v is equal to k5 6, right? And this is B 2 1 2 1 7 k. So u and v are orthogonal, so definitely u into v is equal to 0, right? K k1 dot k5 6, that is equal to 0. So dot product of this two vector, that is k square plus 5k plus 6, that is equal to 0. K plus 2, so the factorization of this equation, we get k plus 2 into k plus 3, that is equal to 0. So we get k is equal to minus 2 and k is equal to minus 3. And B, u and v are orthogonal, again 2 1 2 and 1 7 k. So 2 1, right, 2 1 3 1 7 k. So 2 1 3 dot 1 7 k, that is equal to 0. Dot product of this two vector, you will get 2 plus 7 plus 3k equal to 0. So 3k is equal to minus 9 and k is equal to minus 3, right? So this question is quite simple. Question 5c, second part. Let u is equal to u1 u2 and v is equal to v1 v2 be vectors in R2. Verify that the weighted Euclidean inner product uv is equal to 3 u1 v1 plus 2 u2 v2 satisfied the 4 inner product axioms. So what is the conditions to become an inner product space, right? First condition is commutativity, second is associativity, right? So we have to satisfy each and every conditions to become an inner product space for this inner product, weighted Euclidean inner product. So you can see inner product u is equal to 3 u1 v1 plus 2 u2 v2, that is equal to 3 v1 u1 plus 2 v2 u2, that can be expressed as inner product vu. So commutative law is satisfied clearly. Next is inner product uv w, that is equal to 3 u1 plus v1 w1 plus 2 u2 plus v2 w2, that is equal to 3 u1 w1 plus 3 v1 w1 plus 2 u2 w2 plus 2 v2 w2, that is equal to 3 u1 w1 plus 2 u2 w2 plus 3 v1 w1 plus 2 v2 w2, that is equal to inner product UW plus inner product VW. So inner product U plus VW, that can be expressed as inner product UW plus inner product VW. Also inner product alpha U V, that is equal to 3 alpha U1 V1 plus 2 alpha U2 V2, that is equal to alpha into 3 U1 W1 plus 2 U2 W2, that is equal to alpha into inner product UV. Inner product U with U, that is equal to 3 U1 square plus 2 U2 square, that is always greater or equal to 0. Inner product U with U is equal to 0, then inner U1 is equal to 0 and U2 is equal to 0. So you can see quite easily we can satisfy the 4 exams or 4 conditions to become an inner product space for this inner product weighted Euclidean inner product. So thus all the 4 exams are satisfied of the given weighted Euclidean inner product. So here the complete the solution of this question paper. Thank you.